So no more table of values. We're going to use the two-dimensional graph of 1 minus cosine theta and its critical points to give us a guide. So midline's at positive 1. And it's a cosine, so it starts at a max or a min. It's a negative cosine, so it starts at a minimum, amplitude of negative 1, or amplitude of 1, I should say. Starting 1 unit below the midline, ending 1 unit below the midline, reaching 1 unit above the midline, and then hitting some zeros. Okay, so we have critical points at 0, 0, pi over 2, 1, pi 2, 3 pi over 2, 1, and 2 pi 0. So this graph is going to start at 0, 0. Which is the origin, by our vocabulary standards. Actually, in the polar world, the origin is actually referred to as the pole. Not to be confused with the North Pole.
What about the South Pole?
But certainly I think I could draw a parallel between the pole and the North Pole. So we're starting at the pole. And then we're going to go to pi over 2, 1. Now, I'm going to scale this so that every other circle is 1. So pi over 2, 1 would be right there. To connect these, I'm in quadrant 1 with positive R values. So I'm in a loop through quadrant 1 to connect those. Keeping in mind that this little loop is not to exceed and go outside of this circle with radius 1. Right? Because if you look at our graph, in that little stretch there, we never exceed 1. The radius slowly is getting increasingly higher towards 1, but it never surpasses 1. So this little loop is not to exceed and go outside of that circle with radius 1 yet anyway. As we travel from pi over 2, 1 to pi 2, which is here, our radius is going to get increasingly larger towards 2, but again, it will never exceed 2, so it will never go outside of this circle with radius 2. So I will just kind of let my looping pattern continue. And then I'm going to come back to 3 pi over 2, 1, which is here. I am not going to ever go outside of that second circle. Thank you. And then I'm going to finish at 2 pi 0, going through fourth quadrant angles with positive r's. This is going to traverse through the fourth quadrant before returning to the origin. What's wrong? It is a heart. When we go through limaçons, there's really kind of 4 different shapes we're going to look at, and it's all going to be dependent upon your roots. I'll come back and talk more about your 2-dimensional roots once we see what a different version of a limousin does, and we'll kind of talk about why they don't all look like hearts, but that one is called a heart shape, so we'll come back to that. Let's go ahead and graph this one, which has a midline at 3 and an amplitude of 1. So it starts and ends 1 unit above the midline, has a minimum 1 unit below the midline, and then it's zeros. So we have 1, 2, 3, 0, 4. Pi over 2, 3. Pi 2. 3 pi over 2, 3, and 2 pi 4. So a theta of 0 with a radius of 4. I can't skip in my labeling of the circles this time because I won't run out of room, so I'll just keep it honest. There's 0, 4. And I need to connect that to pi over 2, 3. Now, first quadrant inputs, all positive R values. And the R values are all staying between 4 and 3. So when I connect these, I need to kind of stay in between those concentric circles, the 3rd circle and the 4th circle. Do we see it? Because my radius is constantly between 4 and 3. Then when I go to pi 2, again, all of my radii in the second quadrant are positive. More specifically, they're constantly staying between a radius of 2 and 3. So when I connect these two, I need to stay between circle 2 and circle 3. And then 3 pi over 2, 3. Now my radius is growing again from 2 to 3. And still growing to get me back to my starting point. 2 pi 4 is already plotted. It's the same thing as 0, 4. And my radius is on the increase again. So this one, not so much a heart, right? This is more like a flattened circle, I would say. Steven.
What I was doing last night, because I had a hard time figuring out like the shape and like drawing from perpendicular. Couldn't you just, since the sign goes at the rectangular graphs count by essentially 30 degrees, couldn't you just kind of like guesstimate where 30, 60 are?
Yeah. Oh, yeah. So you could say like 30 degrees would be about 3.8-ish. 60, if you want to be more and more exact, yeah. So when you're looking at these two graphs, what kind of caused this one to be heart-shaped that this one did not have, would you say? What'd you say, Josh? Negative.
Where the cosines reflected.
To be honest, even if this was 3 minus cosine, you wouldn't see a heart shape there either.
Where your roots are.
Say it again.
Where it crosses, like the midline. Like where your roots are.
Your roots, not necessarily your midline. But this one, has no zeros, which is why it never reached a radius of 0, and the polar graph never revisited the origin or the pole. Do you see that? It always had a positive radius, so it never returned to the pole. Whereas this one, not only did it return to or did it hit the pole with a radius of 0 on 2 occasions, it did so at its minimums. Okay, which I'll talk more about when we see a 2-dimensional graph actually hit zeros, but it won't be at the minimums. So we'll see what happens then. But a lot here has to do with how the amplitude relates to the midline. This one has a midline of 3. The amplitude being only 1 never allows it to reach the x-axis. So on this one, I will write, there are no zeros. So therefore, there are no visits to the pole. On this one, there were zeros only at minimums. So we got this heart shape. And that's really because the midline being 1 and the amplitude being 1 kind of made our 2-dimensional graph tangent to the x-axis. So it hit the x-axis, but it did not go through the x-axis and go into negative r's at all. Okie doke. Okay. The next example here has a midline at 1. With an amplitude of 2. So it's going to start on the midline, end on the midline, and have a halfway point on the midline. And then with an amplitude of 2, it's going to oscillate and go 2 above the midline, and also 2 below the midline, which is going to create zeros and is going to create, therefore, visits to the pole or the origin. But also something else is going to happen here, because it doesn't just hit a root of 0 and turn around like we saw on the front side. It actually goes through the x-axis. So you'll see what that does in a minute. So let's label these critical points. 0, 1, pi over 2, 3, pi 1, 3 pi over 2, negative 1, and 2 pi 1. Okay? Now, zeros are critical points. If we wanted to find those critical points, that's where the radius is 0. So I can go up and put 0 in for my radius and figure out where that's happening. Right? Subtract 1 from both sides. Divide by 2 on both sides. and think about inverse functions. What's the reference angle? Pi over 6. And it's where sine is negative, which is going to be the third and the fourth quadrants. So in the third quadrant, it would be at 7 pi over 6. That's this point. 7 pi over 6, 0. And again in the fourth quadrant, at 11 pi over 6, 0. Okay, so to get this graph started, we'll start at 0, 1. Can I scale my graph? I think I can. So I'll call this 1, this 2, and this 3. We'll go every other. So 0, 1 would be right there. And then pi over 2, 3. 1, 2, 3 would be right here. And this is Q1. That's my entire stretch of Q1, which is always with positive r's, ranging between a radius of 1 and 3. So when we go to connect this one to this one, we're going to do so with a loop that goes through the first quadrant. And then our next point is pi 1. So to connect the second point to the third point, again, I'm all quadrant 2, and the entire quadrant 2 is positive. Good? Now, quadrant 3 is trickier because it's this whole stretch in here. The initial stretch of quadrant 3 is positive, right? Before it hits the pole partway through and then becomes negative. So my next critical point is a 0, is a visit to the pole. And to get from here to here, I'm going to have positive r's in quadrant 3. So it's going to be a little subtle loop through the third quadrant. En route to my next critical point, which is 3 pi over 2 negative 1, which is here. So that second stretch of quadrant 3 has negative r values. So if you're a quadrant 3 angle with negative r values, where are you? Quadrant 1. And that's kind of where the flow of the graph is taking you anyway. So to get to that next critical point, to close out our third quadrant, we're going to loop through quadrant 1. Are you with me? Okay. So then we enter into quadrant 4, which quadrant 4 angles start with negative r's. Quadrant 4 angles paired with negative r's are going to put you in quadrant 2. But at some point we're going to hit the pole. So we're going to loop around and hit that pole again, which is technically at 11 pi over 6. And then that very last stretch of quadrant 4 actually has positive r values. So actually will loop through quadrant 4 to get us back where we started. So now, do you see what happens when we have roots And the graph doesn't just touch the root and bounce back, it actually goes fully through the root. We get what is called an inner loop. That's going to happen when your amplitude is larger in magnitude than your midline. Yes? Okay, so anytime we intersect and go through zeros, we're going to have an inner loop, what is called an inner loop. That's going to happen when the amplitude is greater in magnitude than the midline. Okay, jump back to the front side for a second. This is when the magnitude of the amplitude is equal to the midline, right? When the magnitude of the amplitude is equivalent to the midline value. You're going to get that heart shaped. And this one doesn't even come close to having a zero. There's going to kind of be some fine tuning between this example and this last example that we'll talk about once we complete this one. So let's plot this two-dimensional graph, midline at 3. Is this going to have zeros?
No.
No. Because the midline is 3, but our amplitude is only diverging us 2 units above and below that. Going 2 units below at first. And then 2 units above. Critical point 0, 3. Pi over 2, 1. Pi 3. Three pi over 2, 5. And 2 pi 3. I don't think I can scale my circles here either. I don't think I have room. So I'll keep it honest. 0, 3. It's right here. And then pi over 2, 1. And then our radius is on the rise again, back to pi 3. So this one's not so much a flattened edge. This is referred to as a dimple. because it just kind of dips in a little bit, but not all the way to the origin. And then 3 pi over 2, 5 allows that radius to keep growing as we make our way around. And then 2 pi 3 has that radius coming back in as we make our way around. So it's kind of heart-shaped in a way, but heart-shaped ones actually revisit the origin and come to a point at the origin. These dimpled shapes do not. Okay? The difference between the dimpled shape and this like flattened circle is in the ratio of your amplitude to your midline. Okay? Here are the formats for limicons. It's A plus or minus B sine theta or A plus or minus B cosine theta. So the ratio of A to B is the critical piece here. In this first example, A is 1 and B is 1. Agreed? Okay? When that happens, when A over B equals 1, or in other words, if A equals B, those are pretty much saying the same thing, then heart-shaped. What's A in this second example here? Three. What's B? 1. So there's two different cases for when A is bigger than B. Because if you go to your last example, what's A here? 3. What's B? The negative is going to not be an issue. It's plus or minus. So we're just going to ignore the negative. So here we have an A that's bigger than B. And here we have an A that's bigger than B, but they're two different shapes. When A over B is greater than or equal to 2, which it is in this case, then we get this flattened side. Not quite a dimple. Nothing's coming into a point. It's just more of a flattened side.
Kind of like a shield. Oh, okay. One example.
Versus on this one, A is still bigger than B, but the ratio of A to B is somewhere between 1 and 2. It's dimpled. And then lastly, the inner loop kind. A was 1 and B was 2. So anytime A is less than B, or in other words, A over B is less than 1, those are both saying the same thing, then we get an inner loop. And I know we already talked about it, but as far as your two-dimensional graphs are concerned, it has to do with, do we have roots? If so, do we barely touch the root, or are we fully going through the root? And when you fully go through the root, that's what causes inner loops. Okay? You do not need to memorize all of those rules. Some people like to kind of quantify that and what's really the number comparison that's causing these different styles. But at the end of the day, if you're graphing these, your two-dimensional graphs are your guide. Thinking about the quadrants and the size of R, whether R is positive or negative, will lead you to those graphs.